Hello everyone, welcome to our presentation. My name is Jakub Chłędowski and I am one of the members of the NYU B team. Today I will share with you some of the approaches we used in the second edition of the DBTex Challenge. The challenge is to build a system that can localize cancerous lesions in the digital breast tomosynthesis volumes. The example shows slices of the DBT volumes with ground-truth boxes marked as red and model predictions as blue. A blue prediction is considered correct if the slice dimension roughly matches, and the distance between centers of the boxes is less than half of the ground-truth diagonal for 100 pixels, whichever is larger. The goal of the second DBTex challenge is the same as in the first challenge. For this reason, we use the winning solution from the first challenge as a base for our experiments. The solution is based on a 2D efficient net model that uses EfficientNet as a backbone, processes the signal with a BiFPN network, and passes it to two heads, one to fit the boxes and one to classify them. The techniques we used include additional augmentation of the training data, cropping the most informative region, cross-validation, and ensembling. This baseline model works on 2D slices and uses max slice selection algorithm to combine slice level predictions into volume level predictions. More information about our solution to the first challenge can be found on YouTube. In the current second edition of the DBTex challenge, we have introduced several changes to our solution. The changes include the utilization of extra segmentations, copy-paste augmentation, change of the parameters in the focal loss function, and the introduction of an additional classification head. These changes increase our mean sensitivity to 0.957, which reduced our test error from the first DBTex challenge by more than half. In the following slides, I will go through the changes, one by one. First of all, we used additional data provided by NYU Langone Health. DBTex2 training set contains almost 20,000 volumes, with 200 volumes with annotations. In the first challenge, we have utilized the NYU breast cancer screening dataset, containing almost 8,000 segmentations, coupled with the old NYU DBT dataset that contained around 2,000 segmentations. For this challenge, we were able to utilize almost 2,000 additional volumes with segmentations. In addition to affine transformations and horizontal flips used in the first challenge, we have implemented copy-paste augmentation, which works as follows. First, we copy several randomly selected segmentations. Then, after augmenting the segmentations, we paste them onto the training image. This way, we increase the number of positive signals in our training set. Next, we analyzed and enhanced the behavior of the focal loss. The MS-COCO dataset, on which our model was pre-trained, contains on average a much larger object-to-image ratio than DBT. For this reason, the loss function has to deal with a great number of background boxes, with only a few positive ones. As a solution to this problem, we have tuned the alpha parameter in the focal loss from 0.25 to 0.85. This increases the magnitude of the loss for positive lesions, which is indicated as green, and decreases the loss for background boxes, indicated as red. This change punishes the model for not giving enough confidence in positive predictions while lowering the loss for the background boxes. Before we continue with our improvements, let's make a quick break to define intersection over union, or in short, IOU. As the name suggests, IOU between two objects is their intersection divided by their union. For example, the IOU of two separate boxes is 0. The IOU of two highly overlapping boxes is often larger than half, and the IOU of two exactly matching boxes is 1. Our analysis of the focal loss showed that our model received contradictory signals during training. There are two parameters in the focal loss that determine whether a prediction should be considered positive, negative, or not used for loss computation. The first parameter marks the IOU threshold between the prediction and the ground-truth box, below which all predictions are considered negative. The second parameter marks the threshold above which all predictions are considered positive. We do not calculate the gradients for all remaining predictions. Because all boxes with IOU with the ground-truth larger than 0.5 were treated as positive lesions, multiple boxes that do not resemble lesions were wrongly utilized. Similarly, small boxes that reside inside the ground truth box were often treated as negative ones when their IOU with the ground truth was smaller than 0.4. Our solution to this contradictory signal problem is to widen the range between the IOU thresholds. By only punishing boxes that have less than 0.2 IOU, we are able to stop punishing the ones that were good enough. Also, by only rewarding the boxes with IOU greater than or equal to 0.7, we are able to only select boxes with greater matches with the ground truth lesions, thus reducing the contradictory signals. The next improvement is the cancerousness classification goal. Typically, the goal of the efficient debt model is to assign high probabilities to the boxes that have high IOU with the ground truth box. We call this goal objectness classification. This means that the model tries to detect whether the object in the box is the whole cancer lesion. However, since small parts of a lesion are still a lesion, punishing such small box predictions might confuse the model. We mitigate this by introducing a second classification goal we call cancerousness. The main idea in this separate head is to reward all boxes that highlight smaller parts of lesions. For example, if the prediction is outside of the ground truth box, both labels are negative. If the prediction is inside the ground truth box, but with small IOU, we set the cancerousness label to true, while keeping the objectness as false. When the prediction is larger than the ground truth box, but with close enough IOU, we assign objectness to true while keeping cancerousness as false. Finally, when the boxes align perfectly, both labels are set to true. Here you can see some examples of when the model correctly found the ground truth lesion. The red box indicates the ground truth. The intensities of the blue prediction boxes indicate the probabilities assigned to them. Here are some failure cases that the highest probability box returned by our model was not closely matching the ground truth box. Our team consists of a large number of collaborators. JP, Jan, and I worked on the model building. The NYU Lincoln breast imaging section provided us with expertise from the clinical side and lesion annotations. Professor Krzysztof J gave us guidance in model building and managed the collaboration among the entire team. With that, I would like to thank you for your attention.